Hello, Patrik of Cor Power Ocean. We are here just a few days, I think, or a week after you put your full-scale wave energy unit into the ocean.
Exactly. It's a little bit more than a week now of data that we've started to gain on it. So very exciting times.
How nervous were you when you put it in the water?
Well, we made a few attempts before, so we were starting to get reasonably used to it. But of course, leaving it out there for the first time, it's important to check that there's not any major issues, that we're not taking in water, that the anchor is still sticking to the ground, etc. It's all working fine so far.
Tell me about how you put it in place. How do you do it? How do you get one of these into the water?
Yeah, so when you build a wave farm with this technology, you first install the infrastructure, so that you have an anchor for each wave energy device. So we have a new type of pile anchor that we call a UMAC anchor. You go out then with an offshore construction vessel, and then you vibrate this pile into the ground. It takes 10 to 20 minutes to embed this 20 meters into the sand, into the seabed.
So you don't hammer it down, you actually use vibrations.
Yes, and that's a very nice feature to reduce the noise pollution, etc., which is a concern when the standard way is to bang them in, as you say.
And this is something you have also developed.
Yeah, that's something Cor Power, in collaboration with the European partners, has developed over the last 5 years. So started testing in small experiments in sand pits in Germany and centrifuge in the UK, etc., and have gotten to a quite revolutionary geotechnical solution that just this kind of piles, they can take about 5 times more uplift into the seabed than a standard pile.
Okay. So you have that there, you have the cable, of course, going out.
Yep. Then you lay the cables and put the anchor points together, and then it's ready to accept the wave energy device.
How does that work? You just...
and of course, each device, they are 9 meters in diameter. So what we're seeing.
What are we seeing here?
This is a quarter scale.
It's a quarter scale.
Yeah. So you got
something. It's 4 times the size of this big boy here.
Exactly. This is about 2.5 meters. So 4 times as big. The real one, but it's still, it's a reasonably big structure to be on land, but in the ocean, it's a very small thing. So when you compare that to a offshore turbine in wind, it's a mini thing there. And that's the kind of modular approach that we're taking.
It's one of the advantages, really, of what you do.
We keep unit sizes reasonably small, and then we make a lot of them instead. So to install it then, to come to that question, we lift it into the water in a small local port. On land base in Portugal is in Viana do Castelo. And then we use a local tug to tow it down to the site. From there, it's about 30 kilometers. It takes a few hours of towing it. And then when we arrive on site, then we have a wire to the pre-installed anchor. We connect it to the wave device, and then we pull it down to the anchor.
Right. And is all this done by hand, or is it done remotely? How is it actually?
Yeah, I mean, you connect a wire to a tug or a vessel that pulls it down. But then when the bottom of the wave device reaches the anchor, we use a remotely controlled quick connector.
Right.
That first lock in the device to the anchor mechanically, and then there's an electrical connection to power and communication to the shore. And then that starts going through the export cable on the sea.
Right. But it must have been quite a hurrah moment anyway when the electricity started flowing.
Absolutely, where we could confirm that we were installed and grid connected. That was a big moment for us.
Very cool. And as I understand it, you are now testing out all types of scenarios, you could say, right, on the device?
Yes, so we've started the commissioning program, and that goes through many hundreds of different tests to verify the functions of the system. In the initial phases, it's focused on machine safety and survivability to make sure that we can operate safely in any kinds of weather. So we are putting emphasis on that first to make sure that is there. And then once we build confidence on the machine operation, we're going to start letting it do more motion and then start capturing more power.
Right.
So gradually over time, we're going to shift focus towards power performance. But right now, it's machine safety, making sure we can do any weather.
Good. Can you say something about the power performance? How can you do some sort of, I imagine you have, of course, done calculations, but can you say something about it? How will it perform in your estimates.
Yes, of course. So this is the fourth time that we calibrate the model. So we have a very, very tight calibration, we think, between what it's going to be producing in the ocean and what it's estimating in the half-scale machine we had in Orkney. In most sea state, it was a delta of 2 to 3% between predicted production and actual measured production. So the performance with a buoy of 9 meter, 300 kilowatt rating in a site like this, in average in the Atlantic, you can produce somewhere between 100 and 120 kilowatts in average. So a capacity factor of 35%, something like that.
Yeah.
And in our roadmap over time, we expect to be able to take that up to the 40 and the 50% level as well.
Is that because you can utilize more of even the maybe bigger waves as time goes by and get more secure in the... Yeah.
Exactly. So there is room for tuning, and the amount of power that we deliver now compared to what is theoretically possible of a device of this size, you can go even more in the higher waves, and you can also get more power out of the smaller waves by having better and better control of your motion in the wave patterns, and of course also increasing availability of the system, having higher reliability, making sure that you run for almost all hours of the year.
Let's talk a little bit about the power profile and the cost of power, because it's been a lot in the debate recently, the variability of the renewables, and in reality you have a completely different power profile. So tell us a bit about that when it comes to wave power.
Yeah, that is the big role that we see for wave energy here going forward, that when you add wave energy to a mix of wind and solar, you can achieve a mix which is providing 24/7 clean electricity with very little storage and very little overcapacity needed compared to the case where you don't have wave energy. So it can take the kind of role that nuclear and even more fossil sources are taking today to provide that balancing and that stability to the system.
We'll throw in a graph here of the actual power profile. It's very clear when you see it like that in comparison to solar and wind.
Yeah, it's a perfect companion. So in that way, it's really not a competitor to wind and solar. It's really a complement that makes the mix work. Yeah, and then there is, of course, I imagine, a price premium for some of the hours where you are generating electricity, since other systems typically don't. Exactly. I mean, if you have a wind-dominated energy system, take Ireland or Denmark or something like that now, when it's windy, the last thing you want to have is yet another wind turbine, because there's perhaps zero value or negative prices in the market. And then when it's not windy, it doesn't help to have another turbine because it's not generating. So the capture price, which is usually the word used for the average value that you can capture over the year in wave energy, can in many markets be twice as high as another source.
Can you talk about your estimated cost of actually producing that electricity openly?
Yeah. So I mean, we've done, of course, a lot of validation of the actual cost levels of this device and the improvement that we see to our product roadmap. And we need about 600 megawatts to get to a price point of around 70-75 euros per megawatt hour in levelized cost of electricity.
Right. You need that as a total of that park.
Now in cumulative deployment in the market from now when we start deploying until that year.
Okay.
And with our rollout plan now, we hope to get to that point at around 2031.
So I understand.
And that's combining all the deployments we do locally of this technology.
So the learning curve will then lead to
the improvements. And so there's improvements in performance contributing to that. There's reduction in capex, and then there's reduction in opex. And it's coming from cycles of learning where you just do each part more efficiently when you learn how to do it better and better for each cycle. And then there is economies of scale from volume.
From buying more bulk, for example, and things like that.
And more, of course, efficient manufacturing. The bigger volumes, the more mass manufacturing methods we will be using.
And where are you manufacturing it now? I'm pointing to this one.
Exactly.
You should point is having 4 times as big, and you can sort of imagine that it's a big production thing to do it.
It is reasonably big, even though it's small compared to wind. So the power takeoffs, we have a pan-European supply chain. So we have a very large fraction of it being our own unique designs of mechanical parts that we fabricate by metal fabricators around Europe. And then we bring them to our integrator here in Sweden, where we assemble the power takeoffs, the drivetrain, which is sitting on the inside. And then those are shippable on standard road, rail, sea around the world. And over time, of course, we foresee multiple assembly facilities around the world. But it's currently built around Europe and assembled in Sweden. And then it's also dry tested in this dry test facility where we're sitting now.
And this, how is this actually made?
Yes, the composite hull. There we made a pretty big industrial development over this last phase in stage 4 over the last 4 years. So we have developed a quite unique mobile factory technology. And that's much thanks to our Portuguese team of composite experts where we've built up that. So we've developed a mobile factory cell with the machine, and we will be moving the machines to fabricate these hulls to each customer site, produce the amount of hulls needed for that project, and then move the factory cell to the next customer site. So by that, you cut away the cost and the CO2 from transportation. You move the machines instead of moving the product.
Makes sense.
It's a fully automated additive process that we use. So we have a mandrel, and then we weave or spin up these ones layer by layer in an additive automated process. So very, very high level of automation.
It's a lot of different parts of this that has required innovation in themselves to actually make it to where you are now. Can you tell us, just for the average, to be honest, for a guy like me, tell me how it actually, what's the principle? Because it's a bit exciting how this came to be.
It's a nice story there. The background, the inspiration, our initial inventor, Stig Lundbeck.
Let's give him some credit.
Absolutely. Stig has been an amazing inventor. He was a super genius behind some hundreds of patents in so many different fields in
water treatment, for example.
Motors, all kinds of machinery. But he was a medical doctor, not a trained engineer. But he had this brilliant technical vision. He just saw solutions in front of him. So he was inspired by the pumping principles of the human heart when he came up with the initial ideas behind this technology. And the heart has muscle to pump the blood out, but then the return motion, when it refills the chamber to do a new cycle of pumping, there's no muscle to pull it back. Instead, it's stored by hydraulically stored energy. So it pulls the heart back. And he had the same thing with the wave buoy here. So the wave is lifting the buoy upwards, and then return motion is done by stored pneumatic pressure in our case. And by that, we are able to extract the same amount of energy going up and going down. So you make a bi-directional motion from those ideas. And it also provides this survivability feature that we have, that allows us to be very transparent and protected from storm waves in the natural state of the machine. We can be very stiff and very high frequency.
And a lot of the things are inside.
And a lot of the things inside. And then over time, this Stig's initial ideas we then combined with more research. And there's been very important research at the Norwegian NTNU in Trondheim in this phase control technology, how you get the devices to move in this optimal timing with the waves. And there Jürgen Hals-Tudalshaug, who later joined us as lead scientist in Cor Power, he invented something called the wave spring back in 2012, 2013. That's a negative spring that can change the stiffness. So from this very protected system that doesn't move at all in waves and survive the storms that we had from the initial ideas from Stig, we then added in this phase control technology that when we turn that on, it changes the behavior of the machine completely. And it starts moving in sync with the waves, so in very close to optimal timing with each wave coming in.
So you don't have to shut it off completely, like you do wind, for example, when it's too stormy.
So we can tune the device behavior to the incoming wave conditions. So that's really the big thing that we have brought to wave energy in terms of innovation, that ability to tune and detune the device to the conditions.
it's such an enabler for a lot more renewables actually in the grid. So I mean, everybody wants you to succeed, I think. But a lot have failed before in wave power. I mean, in reality, nobody has really made it big in that field.
Yeah.
So the team you have must mean a lot. The people. Tell me a bit about the group you now have.
It is certainly an endurance sport to do wave energy.
Yeah.
So we have some amazing people from all around the world. We are about 80 people now from close to 20 countries now, I believe. And a very good mix between really researchers, deep science, PhDs in different areas in hydrodynamics, control, and similar areas, then combined with industrial engineering and systems engineering over time. And more recently, in the last phase, we've expanded the team a lot more into the operational side, both into the manufacturing with this composite manufacturing team that we have in Portugal, and the operations and maintenance part, how we build these things together, how we install them, and how we operate them in the ocean.
Because it's a lot of areas, it's composites, it's software, it's mechanics, hydraulics, gearboxes, but there's also the waves and the way nature. Do you have expertise in that as well? I mean, somebody's worked with wave energy before, of course, but maybe other people as well that just understand the sea.
No, the hydrodynamic part is the essence of our technology. I mean, every part of this system has been kind of sculptured to the physics of the wave motion. So no part of this system is because a machine usually looks like that and we just built it. Every gram of steel or composite that we have is there to do the job because of the physics of the
how
wave
the ocean
motion.
behaves. So you can't fight that.
Absolutely. So our systems and analysis team has some amazing hydrodynamic competence in these areas, and also led by our lead scientist Jürgen Hals there, who is a respected researcher in the field.
Well, what about the future? What's up next? What's going to happen now? What are your next steps?
So now we are, of course, tuning and building the operational experience with the first C4 there in the ocean. And as we do that in parallel, we are doing all the learnings, and we are doing the design of the next generation machines that's going to be production machines. So the C4, you can say, is our commercial scale prototype. And we are doing one cycle of learning on that, and then designing the C5s, which will be our first production machines. So we're going to install 3 of them next to the C4 and form a pilot array on the Ayudadora site.
And when are those, do you think, going in?
Hope to have them in the ocean late 25 or early 26. And we also going to clock a certain amount of production time on them, or data, to get the type certification from DNV on those devices. That's a key thing to make this technology bankable.
Cool. Are there any other places in the world where you're already thinking about potentially putting them in water?
Absolutely. So in this whole demonstration farm that we do in Portugal, we are doing that, of course, to prove all the functions, the performance, the reliability, etc., together with customers. And those customers are then developing their own sites and their own wave projects in various places. And we are fortunate to have a very nice group of customers working with us today on that. So in the west coast of Ireland, Simply Blue Group is developing a project called the Sersha project, and it's one of the first commercial wave projects, and it's based on this technology. So in parallel with the demonstration of the C5s and the type certification of the technology, that is being developed and being put through all the consulting, so that it should be ready to start receiving machines once we have the C5s demonstrated.
Get it. And let's talk a bit about the customers. Is it typically an energy company, and then they sign up an end customer who maybe wants typically renewable energy for their operations? Or how does it actually work with the customers?
So our customers typically are utilities or project developers, the ones who will be developing the sites, getting them built, and then operate the wave farms. So we sell the kit to them. It's a turnkey offering of the wave energy systems that makes it possible then to extract electricity from ocean waves. And we help them to design the farms We help them to go through all the consulting processes and to achieve, and also help them to design financing packages where that is needed to achieve the final investment decision that then gets us to get the orders and build the machines for it. So these are our main customers, but then over the years we've also realized that the value of wave energy and the power profile that you mentioned before is unique to many big consumers of electricity. So we have started to work much more closely with off-takers in the recent years. So today we are working with a number of off-takers that have ambitions to go towards 24/7 carbon-free electricity, meaning that they want to have each hour of the year provided by clean electricity, not only the hours when it happens to be windier and sunny.
Cool. And what about ongoing? Once it's installed, is it then, I imagine, a service maintenance fee or?
Exactly. So we are offering the kit. Of course, one piece of our revenues is selling the machinery, but then the ongoing service contracts is that we are offering both operations and maintenance services to customers, so we can guarantee you that it's operating to the set performance, etc.
And you have your first control tower here, actually.
We
controlling your first unit.
It's a nice little control center that we have.
Space center, it looks like.
Where we can see real time what's going on in the ocean. We watch out over the ocean, we see inside the machine, and we have the graphical interfaces observing all the sensors in the machine.
Incredible how far you have come already, although of course there's a lot of work left to be done. Anything else anything I've forgotten to talk about with this? No, it's so much to cover, I feel.
It is. It's very multidisciplinary, and since we met last time, I think we've made a big stride in industrializing wave energy. Because I mean, this part of convincing and for ourselves and the rest of the world that there is a technology that really works. That has been a big part of it, and that we already did good advancements on in stage 3, and now we've done that in full scale. But what we've also done now is really show to ourselves and the world how we can deliver this at scale. So with this mobile factory concept and our PTO assembly and the logistics of building large projects has gotten very more developed lately, and we believe that this modular approach where the unit size of each machine is reasonably small, we put them in these high density clusters, is really a neat way to scale up in avoiding some of the bottlenecks that's currently seen in offshore wind, and using a quite high percentage of local supply chain as well.
Because it's a new product category.
It is
in the energy field. It's in reality something that is not at all in place now. So it must be a lot of trial and error with that as well.
We're building a brand new industry.
Exactly.
And it's a massive manufacturing industry that we're building.
I think about when Vestas started, and it has similarities, I can imagine.
Absolutely.
Completely new category.
That
is, it's very cool. One last question, maybe. When you actually one of the challenges must be to get the electricity to shore. How much of a cost is that? Can you maybe piggyback off of some other installations?
It is a fairly sizable chunk of a typical project, which is the electrical infrastructure. Could be 20-25% of a project. So for then offshore wind farms that are being built, there is the opportunity to combine the power output of wind and wave together, and which is especially interesting when you have this complementary power profile. So when you put the two sources together, and especially with the stability of wave energy, you can sell then a power profile to the grid that has higher value in the market. But you can also then share the cost on the capital side of the export cable.
And how far out are you typically? I imagine it depends a bit, but
the installation we have now in Portugal is about 4 kilometers offshore, and we want to find places depth starting from 40 meters and deeper. Probably the economic sweet spot is between 40 and 150, 200 meters, something like that. We can do a few hundred more meters technically, but the cost of the anchoring and the cabling, of course, goes up a little bit to each meter of length or depth that you add to it.
Well, a very big good luck to it. I imagine it's more than luck, but I at least wish you all of that as well in going forward. And thanks so much for coming on.
Thanks for coming and nice to do an update.
Yeah, this is actually our first update of the Big Wheel Show.
Yeah, cool,
Great.
super.
Thanks.